Thank you very much. So we have time for a few questions, and Tom was first, so go ahead.
Apologies, this is a really stupid question. So you're saying most of your estimator is based on the traffic, which is a symmetric quantity.
Yeah.
I'd always associated entropy production with asymmetric, like a flux in one direction not balanced by a flux in another direction. How am I being wrong?
So I think the tricky point here is that we are talking about averages. So once you take averages of things, you can really forget about what was the original symmetry of the quantities that you are averaging out. And but apart from that,
But in general, in equilibrium,
yeah.
do you expect the traffic to be zero? I would have thought
No, it's
no.
negative. It's negative. So at equilibrium, this quantity will be always positive. Imagine
Right.
so the meaning of the inflow rate is basically if you have something that is being trapped by a confining potential, and then you release the potential, then the system will equilibrate and diffuse. So there will be a loss of entropy, and the inflow rate really tells you how much entropy you are going to lose if you switch off this confining potential. Instead, the traffic is just negative at equilibrium. So the idea is that as entropy increases, the traffic increases as well until there is a tipping point where it becomes positive. And positive traffic means that you are actually able to detect non-equilibrium by only looking at traffic. Of course, again, if you have all the degrees of freedom available, you just put everything together and you will get your estimate.
Okay. Okay, I fundamentally don't understand what traffic is then. That's my problem. Okay, fine.
Okay, so more questions. I see we have a question in the chat.
Okay, if you consider only X and Y for the red blood cell, from red blood flickering moment, and can estimate coarse-grained entropy production since it is a linear model. So then you do expect to match it with your sigma. I think they will not match, to be honest. I think it's really two different things. Also because for example, a coarse-grained entropy production by construction will be always positive. Instead, this is a little bit, I have to admit, the weakness of our approach. If you cannot observe all degrees of freedom, then you cannot estimate the inflow rate, which is usually not that important when entropy production is very high. But when it's low, it might be an important contribution. So here, for example, you have a Y traffic component that is negative, X traffic component that is negative. So the max between 0 and this is 0. So your estimate will be 0. Instead, the coarse-grained entropy production, even if it's a lower amount, will be always positive. So I don't think the two will match, which is good. I mean, you can use both. And in that case, you use the best one.
Okay, one last question, Patrick.
Hi, Ivan. Good to see you. I just have one quick question about your first result where you had the curvature of the correlation function. And I think you were also dividing by a component of the diffusion matrix there.
Here.
I think it was later at some point. In your expression for the traffic, you were dividing by
here.
Here, exactly. So you're dividing by DII. So that assumes that you have a constant diffusion matrix everywhere.
Yeah.
Anything one can do if you have a space-dependent diffusion matrix?
I was thinking about thinking about it just a couple of months ago, a couple of weeks ago. But for the moment, I'm just fighting for the review of this one. So I will postpone this treatment to the future. But I think
make it more general, of course, and I guess that there should be a chance to get it.
I hope. I will do it in the future, but for the moment, I really don't know. I don't have an answer for that. Let's say yes.
Okay, thank you, Ivan.
Thank you.
Okay, we are out of time, so let's thank Ivan again.
Thank you.
And Thank you very much. And now we'll go to the lighting talk part of this session. And the first one is by Yikuan Zhang, who will tell us about geometry of optical control in chemical reactions. Please share your slides and take it.
Okay, can you hear me?
Yes.
Okay. Okay, thank you. Zhang, can you see the screen? Okay.
Everything's good.
Okay. Thanks for the introduction and the opportunity to share our recent work. I'm Yikuan, a PhD student from Peking University. And as we know, in stochastic thermodynamics, an equilibrium system is characterized by a well-defined probability distribution. Now suppose each point in this functional space represents an equilibrium distribution of the system. Our goal in optimal control is to find the trajectory connecting an initial distribution to a final distribution within a finite time that minimizes the total entropy production. This requires carefully tuning input parameters such as the driving potential for particle motion or the transition rates in chemical reactions. As we know, the concept of thermodynamic length introduced roughly 14 years ago quantifies the geometric structure of the near equilibrium transitions in microscopic state space. And then with the development of the stochastic thermodynamics, this idea was extended to the microscopic scale through statistical length, capturing fluctuations in small systems. At the same time, such progress has been made in systems with continuous state variables, such as those governed by Langevin dynamics. Yet, far less is understood for discrete state systems, while existing work often derives lower bounds on entropy production or other optimalities. Concrete control protocols remains largely unexplored, which is crucial for real-world application like biochemical reaction networks. So we all know that the optimal control in thermodynamics, we all know the optimal control in thermodynamics originates from heat engine where we get the Carnot cycle. But the living systems take this further. They are built from network of interconnected cycles, local reactions, coupled with upstream and downstream process forming intricate regulatory pathways. A simple and a typical cycle is the three-state gene circuit where the gene has 3 states. State 1 is the open state that can bind with RNA polymers to transcribe. State 2 is the partially closed state binding a Bell repressor protein, and the state 3 is the fully closed state binding a repressor co-repressor complex, which has a much lower dissociation constant compared with that of state 2. The transitions between different gene states are mediated by binding or unbinding reactions in order to switch the gene state from state 1 to state 3, vice versa. The goal of OC is to control the binding rates by dynamically tuning the concentrations of the repressor, co-repressor, and their complex with minimum dissipations. So such a discrete state system is governed by the chemical Messier equation, where Pi is a probability in state I at time t, and the Kij coupled with the external source concentration is a transition probability from I to J. Here we focus on irreducible reaction networks where the optimal control problem involves driving the system from an initial distribution to a final target distribution within a given time by dynamically tuning the transition rate measure K. Note that, as we said here, we consider the situation that both the initial and the final distribution satisfy the detailed balance condition, the equilibrium states. So considering each bidirection reaction has different reactants and can be controlled by different enzymes, its reaction rates Kij and Kji are subject to constraints. Instead of the global dynamical activities, as you know, we impose another realistic local constraints that the summation of the forward and backward rates equal to Cij, the constant local rate capacity for link Ij. And also following previous work, we allow rates to have discontinuous jumps at the start and at the end of the process, so that we can focus on the control dynamics and the entropy reduction within given time tau. In general, solving this optimization problem requires working in the joint functional space of K and P, which involves numerically solving a non-local Euler-Lagrange equation and computationally challenging task. To make the problem more tractable, we adopt a two-step optimization scheme that provides deeper analytical insights into the optimal control protocol, going beyond purely numerical solutions. So inspired by the concept of shortcuts, the first step is to find the optimum K for any given probability trajectory P allowed by the local constraints. Since the chemical mass equation is linear in K, the number of control parameters typically exceeds or larger than the system size N, especially in networks with cycles. There are infinitely many possible solutions for K. Our key contribution in this step is to identify the optimal race K that minimize dissipation. Remarkably, in the adiabatic limit, where the system's relaxation time is much shorter than the control time tau, we derive a Kirchhoff-like law to solve for this optimal race. By substituting this optimal race into the total dissipation, we find that it takes a quadratic form in P. This reveals an underlying geometric structure. The dissipation is governed by a metric tensor lambda, which depends on the probability distribution, network topology, and the capacity of each link. Crucially, this metric tensor naturally incorporates the system's relaxation dynamics. It contains the friction tensor, going beyond just the visual information matrix, as you know. As a result, the optimal protocol follows a geodesic equation under this dissipation metric, and the minimum dissipation equals the squared geodesic distance over tau. So we go back to the Kirchhoff's law. In the adiabatic limit, the dissipation can be approximated by its first order term, which is analogous to the Gauss law for electronic circuit, with Pi the charge and the natural defined current and resistance. Note that the resistance is in inverse proportion to the channel capacity C. As shown in the right figure, for the simple three-state case, since Pi depends on time for changing probability, there is an input or driving current source at each node I with a constraint due to current conservation, which is Kirchhoff's current law. However, here we don't know the branch current Jij, and by introducing a Lagrange multiplier at each node analogous to the voltage, we can solve this optimization problem in the functional space of Jij to obtain the Kirchhoff's law. You solve the variation problem, you get the Kirchhoff's law. Yeah, from which we get the optimal rates, where phi is a function of capacity C and probability P. So there is a little application for the three-stage in circuit. We obtain the optimal protocol and the probability trajectory shown in the right figure. Typically here you can see the jump steps in the protocols at the start and end of the process. Analogous to the electronic circuit, the local rate capacity is in inverse proportion to the resistance, and the lower dissolution constant in reaction path 1, 3 causes a larger cost for direct transition from state 1 to state 3. Thus, the optimal protocol is to drive most of probability flow through indirect paths 1, 2, 3, rather than the direct path 1, 3. Although the state 3 or state 2 is not the target state, P2 accumulate you can see accumulates transiently as it serves as a buffer to minimize the total dissipation. If we remove state 2, the probability has to transport from directly transport from state 1 to state 3 direct, and the energy cost for this two-state model is higher than the original 3-state model. However, as the difference vanishes as k minus x increase, which means the resistance is becomes small, and the difference vanishes. So yeah. So the takeaway message is that okay, my time is short. So here we instead of the global dynamic activities, we impose realistic local constraints on each bidirectional reaction. And we adopt a two-step optimization scheme. For the first step, we derive the Kirchhoff's law in the adiabatic limit, where we can get the optimal rates for any given p. For the second step, we can find we're gonna find the optimal p trajectory, and we find the Riemann geometry directly in the p space. And the metric tensor contains a friction tensor, not just the feature information. And for the realistic, for the real world system, we find that the indirect path and the non-functional transient state